We now discuss the solution of a problem from the section Real Analysis. The problem is related to the concepts of functions of several variables, and there are two questions that are given on the concepts of functions of several variables. In that, this is the first question. This question has appeared in the CSIR National Eligibility Test held on 16th September 2022, and it is a multiple select question, and it is from part C and it carries 4.75 marks. The given question is: consider the function f from r square to r defined by f of x comma y is equal to x minus y whole square into sine of 1 by x minus y if x not equal to y is equal to 0 if x is equal to y. Which of the following statements are true? And we are given four options. Option 1, f is continuous at 0, 0. Option 2, the partial derivative f suffix x does not exist at 0, 0. Option 3, the partial derivative f suffix x is continuous at 0, 0. Option 4, f is differentiable at 0, 0. We are given a function f from r square to r defined like this. We have to discuss which one of the following statements are true. We now discuss the solution of the problem in detail. We have a function f from r square to r defined like this. We will discuss the options one by one. Option 1, f is continuous at 0, 0. We prove that this is so. Mod of f of x comma y minus f of 0, 0 is equal to mod of x minus y square into sine of 1 by x minus y minus f 0, 0 is 0. That is equal to mod of x minus y square into mod of sine into 1 by x minus y. This is less than or equal to mod of x minus y square multiplied by mod of 1 by x minus y, because mod of sine of 1 by x minus y is less than or equal to mod of 1 by x minus y. And after cancellation, this is equal to mod of x minus y. Mod of x minus y is less than or equal to mod x plus mod y. Yes, yes. And we know mod x is always less than or equal to under the square root of x square plus y square. So mod of x is less than or equal to under the square root of x square plus y square. Mod y is less than or equal to under the square root of x square plus y square. In between there is a plus, because mod x is less than or equal to under the square root of x square plus y square, and mod y is less than or equal to under the square root of x square plus y square. This is equal to 2 times under the square root of x square plus y square is less than epsilon whenever under the square root of x square plus y square is less than delta is equal to epsilon by 2. Thus, for any given epsilon greater than 0, there exists a delta that is equal to epsilon by 2 greater than 0, such that mod of f of x comma y minus f of 0 comma 0 is less than epsilon whenever under the square root of x square plus y square is less than delta. This tells you the limit x comma y tends to 0 comma 0 of the function f of x comma y is equal to f of 0 comma 0. This means that the function f is continuous at the point 0 comma 0. Thus, the option 1 is true. So thus we have proved the option 1 is true. We move on to the next option in the next slide. Option 2. The partial derivative f suffix x does not exist at 0 comma 0. Let's see. F suffix x, partial derivative of f with respect to x at 0 comma 0 is equal to limit h tends to 0 f of 0 plus h comma 0 minus f of 0 comma 0 by h. That is limit h tends to 0 f of h0 by h. That is equal to limit h tends to 0 f of h0 is h square into sine of 1 by h by h. This is limit h tends to 0 h multiplied by sine of 1 by h. Limit h tends to 0 of h is 0 and the sine of 1 by h is a bounded function. Therefore, on the whole, limit h tends to 0, h times sine of 1 by h will be 0 because sine of 1 by h is bounded. Therefore, the partial derivative of f with respect to x exists at 0 comma 0 and f suffix x at 0 comma 0 is 0. So in the option 2 it is given fx does not exist at 0 comma 0 but it exists and its value is 0. So therefore the option 2 is not true. Now in the option 4 we have to discuss the differentiability of the function f at 0 comma 0 wherein we also require the other partial derivative, that is f suffix y at 0 comma 0. So we now compute the partial derivative of f with respect to y at 0 comma 0. That will be equal to limit k tends to 0 f of 0 comma 0 plus k minus f of 0 comma 0 by k, and that is equal to limit k tends to 0 f of 0 comma k by k. F of 0 comma k is minus k square, that is k square into sine of 1 by minus k. So limit k tends to 0, k square into sine of 1 by minus k by k. So this will be minus limit k tends to 0, k times sine 1 by k will be 0 and limit k tends to 0 of k is 0 and sine 1 by k is a bounded function. So thus the partial derivative of f with respect to y at 0 comma 0 exists and its value fy at 0 comma 0 is 0. We move on to the next option. Option 3. The partial derivative fx is continuous at 0 comma 0. So first of all, let us take the function f of x comma y and differentiate partially with respect to x, keeping y as constant. Now f partial derivative of f with respect to x at x comma y is equal to derivative of x minus y partially with respect to x, that will be 2 times x minus y into the second function sine into 1 by x minus y. Agreed. And the first function x minus y whole square into the derivative of sine of 1 by x minus y with respect to x, treating y as constant, and that will be cos of 1 by x minus y, and 1 by x minus y with respect to x is minus 1 times 1 by x minus y whole square when x not equal to y is equal to 0 when x is equal to y. Now x minus y whole square cancel out here. Then you will get 2 times x minus y into sine of 1 by x minus y minus cos of 1 by x minus y when x not equal to y is equal to 0 when x is equal to y. Now we have to discuss the continuity of the first order partial derivative with respect to x at 0, 0. For that, first of all, the limit of this first order partial derivative must exist as x comma y tends to 0, 0. First of all, the limit should exist, and that should be equal to the value of the function fx at 0, 0. First, is it existing? So, notice that the limit x comma y tends to 0, 0 of fx x comma y does not exist because limit x comma y tends to 0, 0 of cos of 1 by x minus y does not exist. Therefore, the limit does not exist. Therefore, it is not continuous at the origin. The partial derivative fx is not continuous at 0, 0 because the limit of the first order partial derivative as x comma y tends to 0, 0 does not exist. So, the option 3 is not true. We continue for the fourth one. So, before the fourth one is f is differentiable at 0, 0. And we have already computed the first order partial derivatives of f with respect to x and y at 0, 0, and both are 0. So, let's now recall the definition of the differentiability. A function f of x comma y is said to be differentiable at a given point a comma b if f of a plus h comma b plus k minus f of a comma b can be written as f of a plus h comma b plus k minus f of a comma b is equal to h multiplied by fx at a comma b plus k fy at a comma b plus h times epsilon 1 plus k times epsilon 2, where epsilon 1 and epsilon 2 are functions of h comma k, and epsilon 1 tends to 0 and epsilon 2 tends to 0 as h comma k tends to 0, 0. So we will now get into this definition, and for us a comma b is 0, 0. So this is f of 0 plus h comma 0 plus k minus f of 0, 0. First, let us see what is this one. And this is f of h comma k, f of 0, 0 is 0. And f of h comma k is h minus k whole square into sine of 1 by h minus k. H minus k whole square we have written h square minus 2hk plus k square multiplied by sine of 1 by h minus k. Right. That is equal to h square minus 2hk into sine of 1 by h minus k plus k square into sine of 1 by h minus k. We have separated. And this first one we have written as h of, in brackets, h minus 2k multiplied by sine of 1 by h minus k plus k, in brackets, k multiplied by sine of 1 by h minus k. Agreed. Let's now get into this one. Further, f of 0 plus h comma 0 plus k minus f of 0 comma 0 plus h times f of x at 0 comma 0 plus k times fy at 0 comma 0 plus, yeah, both are 0. Both are 0. This value is already we have written this one. So f of x, f of y at 0 comma 0 is 0. So they are both are zeros are there. So that means this is written as h times fx at ab, k times fy at ab plus h times epsilon 1, this is epsilon 1, plus k times epsilon 2, this is epsilon 2, and this is equal to h times epsilon 1 plus k times epsilon 2, where epsilon 1 is h minus 2k multiplied by sine of 1 by h minus k, which is a function of h comma k. And this will tend to 0 because as hk tends to 0, h minus 2k tends to 0. Sine of 1 by h minus k is a bounded function. Therefore, this tends to 0 as h comma k tends to 0 comma 0. So also epsilon 2 is equal to epsilon 2 is k times sine of 1 by h minus k, which is a function of h comma k. And will tend to 0 as h comma k tends to 0 comma 0 because k tends to 0 and sine of 1 by h minus k is a bounded function. Thus the definition of the differentiability at 0 comma 0 is satisfied. Thus f is differentiable at 0 comma 0. Therefore, the option 4 is true. Finally, the answer to this question is option 1 and option 4. That is the detailed discussion of the solution of the problem from the section real analysis, which is related to the concepts of functions of several variables. I am sure that you have understood the solution of this problem, and I wish you all the best. Thank you.